Hi, I'm George and welcome to part 44 of the Horizon series. Today's launch day after almost 7 years of development. Now, if you just want to see the highlights of the world record flight, then I'll link to a video down below, or just skip further into this one. But if you've been following this project for a while or are even new and you want to know more about this flight, then this video is for you. It runs at a bit of a slower pace but goes into much more detail about launch day prep, the launch itself. We'll also cover some observations and then we'll also have a look at the data from the 3 flight computers that were on board. Anyway, let's get started. Here we are, early morning, ready to head out the day before launch. Normally we would take 1 car out to the launch site, but for this launch we were going to need 6 people and 3 cars to carry all of the gear. The drive from Sydney to Gunnedah was a leisurely 6 hours. We stay at this hotel regularly, so sites like these aren't nothing unusual, and we're again greeted by the motel staff. Ah, it's the Rocket guys again. The first order of business was to unload some of the equipment into our hotel rooms. One room was about to be converted into a rocket workshop.
Do you want me to get you a cheese sandwich?
But, of course, there's no time to rest. We got back into the cars and drove the 40 minutes out to the launch site at Malele.
Yeah, so it goes out at 90 degrees this way.
In order to save time on launch day, we wanted to set up as much of the launcher as possible the evening before.
So, yellow. That goes, I'm getting goes here. Yeah.
The base frame took about an hour to assemble. It's so much easier when you have extra help.
Because it is from the bottom. So some spanner.
Water rockets, hey? Spirit level, and then we'll bring up the launch bit.
We wanted to be sure that the rocket was going to be pointing as vertical as possible to give it maximum chance of going the highest.
That's it.
The actual launch platform with the release mechanism gets mounted next.
One at a time.
The entire rocket rests just on a pair of bolts.
Yeah. But spanner will be.
Which one? The ratchet, yep. Yeah. They pull the frame together.
But first,
Next, the scuba tanks get added to the base. This helps weigh down the launcher as well as helping provide more stability. We did have a second pair of scuba tanks just in case we needed to abort a full rocket. Then the scuba tank cross connect goes on. And because we're in Australia, this is how we hunt for our dinner. Looks like we won't be eating again tonight.
Too much. That's good enough.
With most of the launcher now set up, and with the setting sun, we headed back to the motel. There was little chance of the launcher going wandering in the night. But there's still lots to do before the launch tomorrow. We start off by attaching the fins. These were stowed for the drive up. The same went for the 3 payload bays. We transported them separately in padded boxes. Blue triangle means batteries charged. Red on red. We had charged all of the batteries in Sydney before we left.
Black on black.
There are 23 individual batteries on board the rocket, and we just wouldn't have enough time in the hotel room to charge them all up, and then also assemble the rocket. We just stopped off a couple of the camera batteries. Next up, we needed to attach the 2 pairs of shock cords for the booster. These run on the outside of the rocket so that the booster can come down sideways under parachute, helping increase drag. We were so tight on time before the launch that in my plan I had listed that the correct shock cord lengths would be figured out at the hotel room the night before. So that's what we did. The shock cord simply hooks under the central bracket that stops it from sliding up the rocket. Hopefully that won't happen. Then it was time to pack the 2 main parachutes. This is a lot easier to do on a motel room bed than on a windy table out at the launch site. We have to fold it into specific dimensions so that it fits inside the deployment mechanism. The other end of the shock cord is attached to the top of the booster with a steel pin. Then we can mount the deployment mechanisms to the top of the booster. We even made a small screwdriver so that you could tighten the screws between the booster segments. The camera pod can also be mounted on the booster. And the booster's now ready for tomorrow. Time to find the beds and put them to good use. Tomorrow is the big day. In the morning, it was time to pack the booster back into its box, though this time it would have to stick out the back. It should be able to survive the 40k drive out to the launch site, and the car would be a little bit more stable. It rained pretty heavily a few days earlier, and so the ground was muddy and super sticky.
You're having fun?
Yeah. Yeah. This the sticky stuff.
I felt a great disturbance in the force, as if millions of
Engineers.
they cried out in terror and were suddenly silenced.
It's the path of good intentions.
Let's have a short pause and meet the team. First, there's my dad, Peter. He's helped me design and build the rocket. With many years under his belt designing compressed air equipment, he was instrumental in designing the high pressure launcher. He also machined most of the parts that needed machining for the project. And on launch day, other than helping to prep the rocket and launcher, he was also responsible for filling and actually launching the rocket. This is my son Paul, who helps with the logistics during launch days, assembles the various bits of equipment, helps me remember things that are forgotten, and he's also an expert on rocket retrieval. During launch, he operates the manual emergency abort should the electronics fail. This is his brother John, who operates all the cameras, both video and still, and he shot a lot of this video. This is why you don't get to see a lot of him, because he's always behind the camera. During the launch, he had to manage something like 10 cameras and fly the drone as well. This is my wife Amanda. She helped look after the crew, making sure we stayed hydrated and fed. On launch day, she was on comms with the club LCO and RSO to coordinate our operations and made sure we followed all of our essential checklists. And this is Aidan, John's friend, who came along on this trip to help out as an extra hand. He helped John with some of the extra camera setups. During launch, he was also tasked with GPS tracking of the second stage if it flew out of visual range. Boomerang lessons are still ongoing. And I'm George, just some random guy off the internet. I was mostly responsible for designing and building the rocket with Dad as well as designing the electronics and software for the project. I also tried to keep the project mostly on track as opposed to on schedule. Okay, let's get the rocket prep finished and get it into the air. The first thing we decided to do was to relocate the launcher another 50 meters further from everyone else on the range. This thing will have a lot of energy and there's plenty of open space. The launch controller can now be installed. We normally run it with a 1.3 amp hour battery, but for this launch we switched to a much larger 26 amp hour battery, so it could run all day and it would be one less thing to worry about.
Okay, battery's hooked up. Now we need the kickboard.
Ensure pressure release valves are closed.
Valves are closed.
Okay. Run black Ethernet cable to launch desk. Don't connect.
We'll be about 100 meters from the rocket during launch. If we have a runaway pressurization, we can't turn it off. Pull the yellow one. As backup, we have a couple of physical lines that we can pull to abort the launch. Time to pack the parachutes into the deployment mechanisms on the booster. We didn't do this last night because I don't like leaving rubber bands stretched for too long. This way we do it just before launch. Keep that tight. And hold it. I have to get these two loops. All 4 rubber bands. Fingers gone. Okay, parachute. Okay, how about we try that again? I'll explain a little later why I did that.
So if it all works, the big one will launch on the top, and then when it gets to a certain height, the smaller one will be released and go off on its own, so it's a two-stage.
The booster's now configured for flight. You can see the blue masking tape we added to the shock cord to try and keep it in place on the outside of the booster while it was in flight. I was really paranoid I was going to accidentally snag the shock cord on something.
Hey, it's on the pad at Malay.
Unseal these. That was just a... Yes. It's time to connect up the rest of the hoses between the launch controller, tanks and the launcher itself. These are all high pressure scuba hoses rated to 3000 psi. Okay, done.
Disassemble nozzle seats.
Okay, that's the next bit. The headsets we're all wearing made the communication out on the range so much easier. I'm not sure what their range is, but it's likely 0.5 kilometer. This meant you didn't have to yell and anyone could talk to anyone else at any time, hands-free. And only now will it clear the... there'll be a little white cube of grease. We're coating all surfaces that come in contact with O-rings with grease.
Krytox.
Here we're doing a final clean on all the launch tubes that will be inserted into the nozzles. Because of the really tight tolerances, a grain of sand could wedge itself between the launch tube and nozzle and potentially make things come to a screeching halt.
Paul, can you jumping to the...
Now the nozzle seats get fitted. This is what attaches the launch tubes to the air supply.
Okay.
We made a special spanner to grab the launch tube. Time to fuel up the rocket. This is just regular tap water from the hotel. That's right, we have rocket fuel on tap. And no, the hotel doesn't have blue water. That's just regular food coloring. Makes for more colourful pictures and video during launch.
It just looks awesome when it launches.
And of course, each booster segment gets its own colour.
Right, no more of that for him. I'm not even sure there's water. You know, about the builder did. You know, those really
Fine.
corners of those are so lower down.
Actually, now that I think about it, technically I'm also holding a water rocket, and so we're doing ship-to-ship fuel transfer. Now the launch tubes can go into the nozzles.
Launch tube A. Launch tubes inserted partway.
Okay. Slide cart get rail buttons onto.
Okay, so I can now see we're going to have to relocate the bottom of the pad. I've got it, I'm holding it, I'll be guiding you guys. So the whole pad has to slide over this way, just slightly. Yep, stop. Hit more, hit more. Okay. Really gentle. Stop. And that's rotated into place, yes. Okay, so next, yep. The cart has to just maybe a centimetre. Side move. Bit more. Yeah, that's it. Okay. Undo the brake. Just leave the brake on. Yes. Okay.
Unlock lever.
Lever is unlocked.
Slide cart until nozzle seats can be screwed in the bottom part.
Okay, so give me a hand here, just really gentle, really, really slow.
The whole booster can now be mated to the launch platform.
Okay, so I'm gonna. That one's caught.
Yeah.
Is it on? Yeah. Looks like it's locked too.
I sounded a bit surprised there because it usually doesn't snap in that easily. Here we're securing the launch tubes to the launcher base. They're intentionally loose so that they can move with the booster's expansion.
Yeah, okay. Okay, let's do A. You holding?
Yeah.
Then we can connect up the launch controller to each of the launch tubes.
B, B. And verify height.
Time to get the sustainer ready.
Red thing, so it's over the edge.
But it was soft.
Yeah, so That's kind of to stop it chafing.
Maybe about that tall?
We're going to need to shove that in
This
there.
is the USO Rocketry. We have set up the thing we want to ground test. We'll be able to ground test that now. Thank you. Over.
That needs to go on here. It's a lot easier when it's vertical. A lot harder when it's horizontal. Let's try loading it. So we're going to push now. And it's going to be a pretty strong push.
Do you want me to get to the end?
Okay, try it. It's locked. Okay, cool. Yeah, you can let go. We won't screw it on. It should be tight enough. That should be fine.
Don't walk straight to here.
Walk around it. Before we, so let's orientation here is important. There should be a little arrow here. There's an arrow here, an arrow there. So this is the one we're putting in. Just super slow, make sure it's aligned. There's a, it's got to fit, the fin's got to fit through the slot of the cart. Okay, stop. Here. Here. You do it from that side. Thanks there. Let's grease it. Let's grease the nozzle. Okay, Paul, slide. No, it pops in straight in. Maybe it wasn't open far enough. There we go. Didn't have it lined up. Pull pin, push pin. That's locked. Okay, a checklist item.
Stand rocket up, press water shift.
Now we're getting the rocket set in the arming position. This just makes it a lot easier to get to all of the different locations on the rocket, and we don't have to climb a ladder.
For now, let's lift it up a bit further and move the cart back. Okay. Can you put the brake on? Oh, no. Is that sitting? Yeah. It's not perpendicular. Okay.
I noticed that one of the parachute doors wasn't closed properly. The rubber bands were just stretching a little bit too much. The fix was just to get some tinned wire and thread it over the servo horn the same way that the rubber band would be.
You want to see Dodgy Brothers?
And then just tighten it. This was actually a contingency that we had planned for.
Wire cutters. Can you hand me the wire cutters just sitting on there in the toolbox?
If the door was slightly open, there was a real chance that air rushing past during boost could pull the door open and deploy the parachute.
Get in there.
You gotta have some drama and tension.
Yeah, I mean, so far it's been okay. And hopefully it won't break. This is what stages the rocket. When this wire breaks, it'll tell the rocket, hey, you've started. This is what the wire strippers were for.
I've got them right here.
Okay. Low-tech solution for it to know when the rocket's taken off.
That makes sense.
We can take the blue tape off. That just means battery's charged. Butterflower is the key. Should I pat him? He looks furry. He's the inspector.
Buzz Aldrin.
Buzz Aldrin, there you go. The rocket on.
This ladybug and
Now we have to run the wires from the release servo to the launch controller. This will release the entire rocket.
There's some tape. Safety tape. Make sure everyone has their safety squints. So where are we in the checklist? Take photos, stand it up.
Check vertical alignment of rockets. I
All
don't
right.
think it's stand it up.
All right, let's go stand it up, Paul.
Now that there's more weight on the pad, we need to check vertical alignment again in case some of the launcher had settled into the dirt.
Turn on launcher computer Raspberry Pi.
The checklist we're following is 3 pages long.
Test fill motor.
Yep,
Test vent motor.
yep.
Let's have a look at some info about the rocket as it sits here on the pad. The dry weight of the booster is 9 kilos and the sustainer is just over 1.5. The booster has an internal volume of around 31 litres and the sustainer just over 7. The booster uses 3 nozzles almost 20 millimeters in diameter and uses 2.8 litres in each pressure chamber, while the sustainer uses 2 litres of water and a little bit of shampoo. The combined total impulse for the whole stack is almost 2,500 newton seconds. The peak thrust of the booster is over a metric ton, while for the sustainer it's a mere 230 kilos. And for the model rocketeers amongst you, the solid motor equivalent for the booster is 3 J1400s, and the sustainer is an almost I800. And at liftoff, the total weight of the rocket including water is 21 kilos or 46 pounds.
This is George. Yes, Brad, we're just about to start the arming sequence. Not pressurizing yet, but we're going to start arming. As soon as we're done arming in about 5 minutes, then we'll start pressurizing.
Okay, copy, thank you.
So the rocket is now fully prepped. We're about to go hot and start arming systems and start cameras recording.
Wait.
You also have to remember that you're on an active range, so you need to look up occasionally. We first lower the rocket so that we can get to all of the systems. The sustainer payload gets armed first.
careful walking there, Mum, with the cables. Short press and then a long press. On the battery itself at the back.
Okay.
There'll be 3 like
GPS
flashing green lights, Mum.
So I'm going to arm this thing, and hopefully it won't shoot off. It's fine. I've checked it. It should be okay.
Camera.
Okay. Yep. GPS. So we have GPS lock. Camera's recording.
Okay.
Yep. Powered on. Armed.
When everything's running, we screw down the nose cone.
Yes. GoPro recording. Hello.
And now for the booster. Here we're arming the parachute deployment mechanisms. A late scrub during this sequence would mean scrub probably until tomorrow to recharge everything.
That's as locked as it can be. Okay. Pod A is on. No stick.
In your pocket, Dad.
This is when your heart rate starts to climb a little, because now you're on a timer and you no longer have the luxury of long pauses to fix something.
Slow, really slow. We don't want to trigger the... Watch records.
Come on, where's that?
No, that's fine.
Yep.
So one shrill swoop. We should. We should hear another shrill fairly soon. And work.
Okay, so everything's armed, cameras are rolling, and we're doing our final checks. One item on the checklist is to manually activate the fill motor at the launcher and fill the rocket to about 50 psi to check for any leaks. The motor tries to open the valve, but nothing.
Do you see any pressure? Why isn't it letting pressure in? I'm going to let in a bit of pressure. Nothing? I'm turning the valve on. What's going on? There's no air flowing. Oh, here we go, here we go, here we go. Oh, the screws come loose.
Then I noticed that the lever arm attached to the valve has slipped. This worked in the earlier test, but without pressure. This is the culprit.
I need a pair of pliers to really tighten this screw.
So I have the boys go grab me a set of pliers so that I can really tighten the grub screw to prevent the lever arm from slipping. With the arm now fixed, the motor is able to open the valve, but now the spring that shuts it off is not strong enough to fully close it, and I have to shut it off manually. Crap, it's always the valves. Otherwise the rocket looks good and there's no leaks. The time is ticking, so executive decision time. We were originally planning to fill the rocket in bursts over about 10 minutes to let things cool down between bursts. Since we now could open the valve remotely, but didn't have the ability to shut it off completely between those bursts, meant that we were just going to have to let it fill continuously, and when it got to 1000 psi we would launch.
Alright, so we're ready to pressurize. Yep. Brad, we're about 1 minute from pressurizing.
So we retreated back to the launch table about 100 meters away to start the pressurization. Now we still had the ability to abort and depressurize the rocket, so we agreed it was safe to proceed. Heart rate is going up at this stage. Then someone noticed a person out on the range heading in the rocket's direction. Luckily they were still a long way out, and with some not so subtle words of encouragement, they changed direction to head away from the rocket.
Last minute panic.
It was one of those wayward boats on the range type of deals. With the range now clear and rocket ready to go, we opened the valve and watched the rocket fill.
Okay. Let's pressurize.
And we were all getting pretty excited now.
What is it now?
Now it's 650.
Are we halfway there?
Yeah, more than half.
Halfway through.
700, 800,
800.
850,
850.
Okay.
1000.
Launching in 5, 4, 3, 2, 1, go!
Oh my God.
Oh. 2, 1, go!
The rocket took 2 minutes and 18 seconds to reach 1000 psi.
Three, 2, 1, go!
This video was shot by one of the uni students. Being further back, it gives a good perspective on the speed of the second stage.
Oh my that a two-stage water one?
Yeah, just wait, is it? Yeah, it is. Okay, cool. Oh shit, look at this. That is crazy.
Nice.
These couple of videos show the nice color in the water. In this video, watch for the water exhaust from the Sustainer.
How awesome was that? Look at where the booster's going to land.
Yeah, where's the second one though?
The low wind conditions on the day meant that the booster landed within about 50 meters of the launcher.
Keep an eye out for the second stage, please, everybody.
Parachute's out. Oh yeah, shoots out.
Oh yeah!
Awesome.
Oh, it's coming right to us.
Yeah. Is the GPS working?
Yeah, I'm working great.
Oh, the moon. The moon right next to it.
Oh, wow.
It's gonna land in the car.
No, let's just go close.
It's gonna land perfectly inside the car.
You could have saved some weight and not put a GPS, couldn't you?
I think we know where it is.
Okay. Are we going to be able to do a second launch?
Yeah.
This was a
Well done,
one-off.
George.
Amazing.
Sorry for the...
Good job, George. Well done.
You just didn't know if it was going to go that way?
The Sustainer landed only about 100 meters from the launcher itself. This was one of the easiest retrievals we've had. All the data about the flight, like altitude, speeds and other events, are at the end of this video.
Okay, let's hear the beeps. One, two, three. One, three. 5313.
Yeah.
What do we think, Mr. Katz?
I think we did it.
So that's 5,313 feet or 1.62 kilometers and just over a mile. We believe this to be the new world altitude record for water rockets. The previous record of 3,155 feet or 961 meters was set 5 years earlier by this very second stage when it was flown at 1150 psi by itself without a booster.
Good tape that.
We're trying to listen to the beeps but can't tell anything because both flight computers are beeping. The booster survived well without any damage at all, and the soft ground meant that it was gentle on the fin that it landed on.
Should we film how much?
You can see how close it landed to the launcher. It was a short walk back to home base.
Slippery because of the foam. You've got to get a typo if you want to do the 5-6. Okay. Thanks, okay.
Then we had to go through another checklist just to power everything down.
Cool. It was recorded? Yep. GoPro still going. I'll need to turn that off.
Congratulations.
5,500.
Yeah, 5.3 something.
5-3, wow.
It's amazing.
Really cool.
The recorded data. That's what it's beeping out at the moment.
Oh, that's spectacular. So glad it went well for you.
Although the maximum altitude was beeping out, we wanted to confirm it first with the logged data. And we'll have a look at that data soon.
Probably on landing. Just going to be GPS. Where's your switch? Oh, there it is.
In all the excitement, we forgot to turn off the air to the launcher. So let's have a look at some observations in no particular order. When the rocket releases, all the hold down force of around 700 kilos is transferred straight through the launch tubes into the launcher. Here you can see how much the launcher, even with such a wide base, gets pushed into the ground. As the rocket was pressurized, you can see how much it flexed on the launcher. Here it is bouncing between zero pressure and full pressure. As the rocket was being pressurized, there was a very loud pop. I suspect it must have been some fibers of one of the pressure chambers that must have let go. You could hear it from a long way away. But it was all good. There was a small leak at full pressure. We're not exactly sure where it came from, but likely from the second stage nozzle or stager. This was Dad's experiment. We've seen what kind of damage the high pressure blast of water can do during a launch, and so he wanted to see what would happen to these toy cars underneath the rocket. It turns out most of that blast was directed away from the cars, so they only got soaked. As the rocket launches, you see a contrail form soon after the water runs out. This is because the air temperature inside of the rocket drops to well below minus 100 degrees Celsius, and it forms a condensation trail. When the cold air runs out, you still see a small stream of water. Now this is an intentional safety feature. Instead of having a sealed non-return valve on the second stage, we have this tiny 1mm hole. After launch, the second stage slowly leaks through this, so that if the rocket didn't stage, it would completely depressurize after about a minute, and that way we could approach the rocket safely after landing. You saw the parachute door on the booster automatically open during preparation.
Parachute.
Now this was caused by the rubber bands not being properly oriented on the servo motor. This is normally how it should be, with each side of the rubber band on either side of the servo pivot point. This way you can have as much tension on the rubber band as you like, but it won't make the servo horn move. When it's self-released, we had that rubber band like this, with the servo horn not quite turned properly. To release the parachute, the servo simply has to turn like this, and the rubber band will slip off. On the fill valve problem, we suspect what caused this issue was that these tanks were pressurized to 240 bar, a safe pressure for the tank, but higher than the normal 207 bar. This increase in pressure would have put extra strain on the valve spindle, increasing friction. Normally when we did tests with the launcher, the pressure was typically somewhere between 2,500 to 3,000 psi, not the 3,500 psi we had here. With the higher friction, the spring wasn't able to pull the valve shut completely. Okay, so let's have a look at the data from the two quantum flight computers that were on the booster. Here we have the altitude plot from one of them, and we can have a look at the altitude plot for the second one. And you can see they correlate quite well, just goes to show how fairly accurate those are. So if we have a look at the overall altitude, the peak altitude for the booster was 1,282 feet, which is 390 meters. Now that apogee happened after, let's have a look, about 8.2 seconds is when it reached apogee. Next thing we can have a look at the total flight time. That was about 1 minute and 10 seconds for the entire flight. We can also see when the parachute ejected. That happened just past apogee. You can see that little spike there. So we can have a look how long it actually took before the canopies fully opened. And we can see there it's about 3.4 seconds. That also happened at an altitude of about 1,110 feet. And that's about 338 meters when it fully opened. So let's have a look at the maximum speed here. So let's turn on speed. So this is speed of one of them. And you got to remember that the speed is derived from altitude. So this is the other one. And again, they match fairly closely. There's a slight discrepancy between the top speed. So if we're going to have a look at the top speed, let's maybe average it between these two. We're going to say 484 feet per second, which is about 530 kilometers an hour, or Mach 0.43. Now, in terms of acceleration, that's kind of hard to derive from this data. It's quite wildly inaccurate. But the altimeter, one of the altimeters says 45G, the other one said 23G. I'm not pointing at acceleration here, but simulation also predicts around 45G. So that's the acceleration value we're going with. Now, the other interesting thing you'll notice here is this little bump in the altitude, and that's actually when staging happened. And so let's have a look at the staging time from the start. Let's turn on this, that'll help. And we can see staging happened right around here, just over 1.4 seconds after launch. Now you'll notice the acceleration, the speed data also has this large spike in it. That is probably not a real spike. There's all kinds of funny things happening during staging. So whether there's high pressure air blowing past the ports, or whether there is any shock waves that are happening in the airframe. So we can safely ignore that spike in the actual speed. But we're going to, you can see the data, how it interpolates. We can interpolate it through like this. So at the time of staging, around here, let's say around 260 feet per second, it gives us about 285 kilometers an hour. Which is quite a speed drop from the top speed here. Normally you'd want to stage at the highest speed possible, but that would have been fairly close to the ground. That would have been maybe 120 feet or something. And to make it look better, we delayed the staging to stage at a higher altitude. You're also trading some drag, so you're not going super fast, and you've gained some altitude, so it's not that much of a loss. But yeah, so that was the decision we went with, to stage at around the 1.4 second mark. And from the speed data, we can also have a look at the descent rate under the two parachutes. That turns out to be about 20 feet per second, or about 6 meters per second on the way down. So that's the booster. Okay, so let's have a look at the data from the stratologger that was on the second stage. Here is our altitude plot. And from this plot, we can see that the maximum altitude was actually 5,313 feet. And 5,313 feet is 1.62 kilometers, or just over 1 mile. And let's have a look how long it took to reach that altitude. Turn on our timing here. And that was around 16.4 seconds is when it reached apogee. Now from here we can also see how long the whole flight took, and that was just around, let's measure it, 220 seconds, which is 3 minutes and 40 seconds was the total flight time. And the descent rate here was around 26 feet per second, or 7.9 meters per second. So it came in a little faster than the booster. Now, one of the things you'll notice here is this noisy data at the very start when we launched. We're not exactly sure what's going on here with that big spike, and I can turn on the booster altitude for comparison. Not the speed. Here's the booster. So actually this is a good comparison to see booster altitude versus the sustainer altitude. But you can see both the stratologger tracked fairly closely with the launch of the first stage, but then something, don't know what happened right around staging. This could be some kind of side effects of the way that the nose cone is vented, where the barometric sensor is. And then you can see up here, there's a couple of steps, I think, where the stratologger is catching up. Maybe it's running some kind of a filter. And then back here, we get a nice parabolic arc. So I believe the data is correct from that point on. If we were to try and derive velocity from this curve, I think that would be erroneous. So what we did, we created a interpolated value, what we think the data should look like. And basically we took it from when staging happened. So we continued the data until staging happened, and then tried to match the curve, the original trajectory. And we believe this is much closer to what the sustainer actually did versus this stratologger artifact that we see. So let's have a look at the velocity. So let's have a look at the raw one from, and mind you, this is averaged, but this is the speed that the stratologger gave us based on what we think is that faulty data. And that's giving us a peak speed of 1400 feet per second, which I believe is incorrect. So let's have a look at the average speed for the interpolated data, and we believe this is a lot more accurate to what actually happened. And we can have a look here, and the peak speed is around 890 feet per second, which translates to about 977 kilometers an hour. Or 607 miles per hour, and that's Mach 0.79, so very close to Mach 0.8, which is the start of transonic. So we thought that was pretty cool, that's what the rocket reached. Now again, in terms of acceleration, because this is interpolated data, we're not going to get a value anywhere near enough. It's just way too noisy. The simulations, when the rocket flew by itself, the second stage, was around 70 G. So we believe, because here it was going a lot faster when it's released, so there would have been extra drag on it. We're going to say somewhere in the region of 50 to 60 G was the acceleration for the second stage as it left the first stage. So that's pretty much it in terms of the data from the flight computer that was on board the sustainer. So that's it. We're so happy how this project turned out. Although it did take a little longer than expected, we hope you enjoyed the journey. We wanted to say a big thank you to members of the New South Wales Rocketry Association who've been very supportive over the years. We wanted to say thank you to Derek Waterman, who did some still photography for us and let us use his GPS tracker. Also thank you to George Holland, who did the welding for the release head for us and acted as a sounding board for ideas. And also thank you to Aidan Barker, who helped out with launch day operations on the day. But the biggest thank you goes to you people on the internet here. Without you, this project wouldn't have been so much fun. Thank you so much for leaving maybe just a thumbs up on a video or taking your time to leave a comment. That's really, really appreciated. So thank you. Now, there will be one more video in the series that will go over how much this thing actually cost. And one big last announcement, because records were meant to be broken, we've decided to release all of the data, all of the CAD files, STL files, any tech drawings that we have on this project, in the hope that the next team that's coming along to try and break this record will use it as a reference. So I'll leave a link to that repository down below. Anyway, thanks for watching, and we'll see you next time.